So before we wrap up on the SR and the S models for the MOSFET and switches and building digital circuits using the switches and MOSFETs, I would like to make some observations. Hopefully these will convey some very interesting insights, particularly those that relate to the connection between the analog world and the digital world. So first of all, notice that the switches that we've been dealing with so far are nonlinear. When you built a circuit containing a switch, even the very simple inverter that looked like this, V in versus V out, notice that the transfer curve that you got looked like this. So this is clearly nonlinear. Okay, this is not a straight line. It is piecewise linear. In other words, it's linear in pieces, but it is not a linear curve. This is non-linear. So when you build circuits using switches and MOSFETs and so on, you end up with a non-linear behavior, and these are not non-linear devices. However, one of the interesting facts is, notice that for a given setting of the switches, okay, so say for example, I pick a given set of values for A's, B's, and C's. Let's say I pick A equal to 1, B equal to 1, and I pick C equal to 0. Notice that what I get here is a set of switch values that look like this. For this part of the switch, I get the on-state resistance, B is 1, so I get R on here, and this is 0, so I get a open connection up here. Okay, notice that for a given set of switch values, given set of control values, A equal to 1, B equal to 1, and C equal to 0, notice that what I'm left with is a linear subcircuit. This is a remarkable result. This is really nice. What this says is that I can actually use my linear techniques, my big bazookas, the superposition and Thevenin and so on, to analyze these subcircuits. Okay, so if I generally take a digital circuit and pick a set of values for the inputs, such as A's, B's, C's, and so on, and then for that set of values, I replace the switches with their either on states or off states, then the resulting circuit is commonly linear, and all my linear techniques will apply. Okay, this is a pretty nice insight. The second thing I want to talk about is something that we will commonly do for circuits is look at the power consumed by our circuits, and power is becoming a really big deal in our field, and in fact the consequences of power are driving the way we are building digital designs today. And so one of the things we'd like to do is analyze the power consumed by our digital circuits. Power is becoming extremely important in data centers and other places where almost a third to a half of the cost of operating a large data center, such as those you might find with Google or Facebook and so on, that maintain all of these computers. When you do your go on Facebook and so on, Facebook has these huge data centers that contain millions of computers. They're all burning power, and it costs a lot of money. And so the amount of money can be extremely large, and so power is extremely important for that and many other reasons. So let's try to understand how to compute power for our digital circuits. So let's go to our example here where I set A equal to 1, B equal to 1, and C equal to 0, and I get my subcircuit. You should be able to directly write the power from here, but if you really want to, you can go and simplify it a little bit just to make it a little cleaner. If you want, you can do something like this. So this is R on, this is R on, and this is RL, and I get A equals 1, B equals 1, controlling the two MOSFETs. And then since the other leg of the circuit is an open circuit, I don't have to show it. So what is the power consumed by this circuit? Okay, and back to basics. The power here is simply given by the voltage squared divided by the resistance. Okay, so here the power is given by V squared divided by 2R on plus RL. Okay, and this is simply, not surprisingly, Vs times the current I. And so if you have the current I flowing through here, that is the power. And I, in turn, is given by Vs divided by 2R on plus RL. And so therefore, notice that this expression is the same as this expression when you substitute for the current. So notice here that the power, interestingly enough, relates to Vs squared. So the power supply voltage relates to the square of the power supply voltage, and this is pretty common in our digital circuits. And so although for pedagogic reasons we commonly use Vs equals 5 volts in this course, because of this huge power consumption and the power issue, modern day circuits have kept reducing the voltage Vs over the past couple of decades. And in fact, today it is not uncommon to see a Vs in the order of zero point 0.7 volts or zero point 0.8 volts. Okay, we've come down substantially. So notice that the power when Vs was 5 volts was proportional to 5 squared, which is on the order of Vs squared or 25. And when I go to Vs, which is almost 1/7 that of 5 volts, I've managed to reduce my power by a factor of 49. Okay, so this is 1/7 the power supply voltage of the past, and the square of that is 1/49th, and so therefore by keeping on reducing the voltage, I've managed to reduce my power by close to a factor of 50. Notice that when I reduce my voltage Vs, I have to modify my devices to also reduce Vt. So commonly, if Vs is 5 volts, our Vt that we used to be about 1 volt. But in today's day and age, when power has gone down to 0.7 volts, the VTs that we use may be on the order of 0.3 volts to about 0.5 volts. So VT is tending to become closer and closer to VS in modern day circuits. But for most of 6002X, for pedagogic reasons and to keep our math simple, we will commonly use Vs equals 5 volts and commonly use Vt equals 1 volt unless specified otherwise. Okay, so before we wrap up on this, I'd like to show you a quick little demo to show you that both analog and digital signals and components are everywhere. You will find gates and digital circuits, oftentimes juxtaposed with analog circuits, and these are called mixed signal designs because they have both analog and digital stuff. And so stand by and let's have a little bit of fun.